Hello, and welcome to the Nocturnal Astronomer. I'm your host, Atlas Reid, and tonight we're embarking on a gentle journey to the outer reaches of our solar system. We're going to explore Neptune, the eighth planet from our sun, a world of deep blue mysteries and hypnotic storms that drift across skies we can barely imagine. Neptune sits nearly 3 billion miles from Earth, so far away that sunlight takes more than 4 hours to reach its cloudy atmosphere. This distant ice giant holds secrets that astronomers have only begun to understand, from winds that race faster than the speed of sound to a moon that orbits in the opposite direction of nearly everything else in our solar system. We'll discover why Neptune appears such a striking blue color, what it's truly made of beneath those swirling clouds, and how this planet generates heat from deep within despite being so incredibly far from the sun's warmth. Tonight, we'll move slowly through Neptune's story. We'll talk about how it was discovered not by seeing it first, but by mathematics and prediction. We'll explore the strange seasons that last for decades, the faint rings that circle this giant world, and the fascinating moons that accompany it through the darkness. We'll consider what it might be like to descend through Neptune's atmosphere, passing through layers of gas and ice until the pressure becomes so intense that diamonds might rain from the sky. This is a place for curiosity and calm. Whether you're settling in for the night or simply want to let your mind wander among the planets, I hope this journey brings you a sense of wonder about our cosmic neighborhood. If you enjoy these types of videos, I'd greatly appreciate it if you'd give this a thumbs up and consider subscribing to the channel. It helps others find these peaceful explorations of space. I'm also curious, where are you watching from tonight, and what time is it where you are? Feel free to leave a comment and let me know. Now then, let's dive in. Neptune's discovery in 1846 represents one of the most elegant achievements in the history of astronomy. Unlike the planets known since ancient times, Neptune was found not by accident or systematic searching, but through the power of mathematical prediction. This story begins with Uranus, the seventh planet, which had been discovered in 1781 by William Herschel. After Uranus was found, astronomers carefully tracked its motion across the sky, comparing their observations with predictions based on Newton's laws of gravity. Everything should have worked perfectly. The mathematics of gravity had already proven themselves by predicting the motions of all the other known planets with remarkable precision. But Uranus refused to cooperate. It wandered slightly off course, arriving at positions in the sky earlier or later than calculations suggested it should. By the 1830s and 40s, these discrepancies had become impossible to ignore. Uranus was straying from its predicted path by amounts that exceeded any reasonable measurement error. Two possibilities existed. Either Newton's laws of gravity broke down at such great distances from the sun, or something else was out there, an unseen planet whose gravity was tugging on Uranus and altering its orbit. Two mathematicians, working independently on opposite sides of the English Channel, chose to believe in an unseen planet. In England, John Couch Adams performed calculations to determine where such a planet might be located. In France, Urbain Le Verrier did the same. Both men worked backward from the observed irregularities in Uranus's motion, using gravity's mathematics to predict where the hidden world must reside. Le Verrier finished his calculations first and sent his predictions to Johann Galle at the Berlin Observatory. On September 23, 1846, Galle pointed his telescope to the patch of sky Le Verrier had indicated. Within an hour of searching, Galle found Neptune, less than 1 degree away from its predicted position. The planet had been found with mathematics before it was found with eyes. This discovery validated not only Newton's laws, but also demonstrated the profound power of mathematical reasoning. Here was proof that the universe operated according to principles humans could understand and predict. The success of finding Neptune through calculation alone inspired astronomers to believe that other hidden worlds might exist, waiting to be discovered through similar methods. Think of it like hearing a note in music you cannot quite identify. You know the sound exists because you hear it, but you cannot see what instrument creates it. By understanding how different instruments produce different tones, you could deduce which instrument must be playing even without seeing it. This was Neptune's discovery, a cosmic note identified by its gravitational influence before anyone had actually laid eyes on the instrument creating it. The finding of Neptune pushed the known boundary of our solar system outward by more than 1 billion miles in a single night. It transformed our understanding of the Sun's family from 7 planets to 8, and it showed that even in the vast darkness of space, nothing truly hides from mathematics. When you look at images of Neptune, the first thing you notice is its color. The planet glows with a deep, rich blue unlike anything else in our solar system. Even Uranus, Neptune's near twin in size and composition, appears as a much paler, greenish blue. Neptune's vivid color comes from methane in its atmosphere, but there's more to the story than simple chemistry. Sunlight contains all the colors of the rainbow mixed together. When this light reaches Neptune, it encounters an atmosphere made primarily of hydrogen and helium, with a small amount of methane mixed in. Methane molecules absorb red light very efficiently while allowing blue light to pass through or scatter back into space. This selective absorption means that the light bouncing back from Neptune toward our telescopes and cameras is predominantly blue. However, scientists have discovered that methane alone cannot fully explain Neptune's intense blue color. Uranus has roughly the same amount of methane in its atmosphere, yet it appears much paler. Research published in the past few years suggests that another substance, possibly a haze of photochemical products or another compound formed high in the atmosphere, enhances Neptune's blueness. The exact identity of this additional component remains a subject of ongoing investigation. Neptune's atmosphere extends thousands of miles deep, gradually becoming denser as you descend. Near the top, where space begins, the air is thin and hazy. Deeper down, the atmosphere becomes thicker, forming distinct cloud layers at different altitudes. Some of these clouds are made of methane ice crystals, similar to how Earth's clouds are made of water ice and liquid droplets, but existing at temperatures that would freeze any water solid in an instant. The planet's appearance changes depending on the altitude and thickness of these cloud layers. High-altitude clouds appear as bright features against the darker blue background, while lower clouds seem darker. The Hubble Space Telescope has captured images showing bright, white methane clouds casting shadows on the deeper cloud layers below them, revealing the three-dimensional structure of Neptune's atmosphere. Temperature plays a crucial role in creating these cloud layers. At the very top of Neptune's atmosphere, temperatures drop to around -360 degrees Fahrenheit. This extreme cold would freeze almost any gas, turning it into ice crystals. As you descend, temperatures gradually increase due to the mounting pressure of all the gas pressing down from above. Imagine descending into an ocean, but instead of water, you are moving through an ocean of gas that slowly becomes thicker and thicker. Near the surface of Earth's ocean, you can see light filtering down from above. Deeper down, the water takes on a blue-green tint, and eventually, all light fades to darkness. Neptune's atmosphere follows a similar pattern, though the details differ dramatically. Instead of water blocking light, you have layers of methane haze and clouds, and instead of a solid seafloor, you eventually reach a transition zone where the gas becomes so dense and hot that it behaves more like a liquid. The blue we see is thus a message from Neptune's upper atmosphere, a specific signature created by the chemistry and physics occurring in those highest, coldest layers. Every photon of blue light that reaches our eyes has survived a journey through Neptune's atmospheric filter, carrying information about the composition and structure of this distant world. That vivid blue is not just beautiful. It's a scientific treasure containing clues about the planet's nature. Despite its name, Neptune is not actually made of ice as we typically think of it. When astronomers classify Neptune as an ice giant, they're referring to a definition of ice that differs from frozen water in your freezer. In planetary science, ices are materials that freeze at relatively low temperatures, including water, methane, and ammonia. Inside Neptune, however, conditions are so extreme that these materials behave in ways entirely unlike ordinary ice. Neptune's interior structure consists of three main regions. The outermost layer is the atmosphere we've already discussed, extending down several thousand miles and making up only a small fraction of the planet's total mass. Below this lies a vast mantle of hot, dense material sometimes called the ice layer, though calling it ice is misleading. Here, under immense pressure and at temperatures reaching several thousand degrees, water, methane, and ammonia exist in exotic states of matter. Think of it like this: if you squeeze water hard enough and heat it sufficiently, it stops behaving like either liquid water or solid ice. Instead, it becomes something in between, a superionic state where oxygen atoms form a crystalline structure while hydrogen atoms flow through that structure like a liquid. These conditions exist deep within Neptune, creating materials with properties we're only beginning to understand. The mantle extends down about 8,000 miles from the cloud tops and contains most of Neptune's mass. The pressure here reaches millions of times Earth's atmospheric pressure. At such pressures, methane breaks apart into carbon and hydrogen. Some scientists propose that the carbon atoms then bond together under the extreme conditions to form diamond crystals. These diamonds would sink slowly through the surrounding material like snow falling through air, except this snow would be made of gemstones drifting through hot, dense fluids. Laboratory experiments have attempted to recreate these conditions using powerful lasers and diamond anvils that squeeze tiny samples to extreme pressures. These experiments have confirmed that diamond formation is possible under Neptune-like conditions, lending support to the idea of diamond rain in the planet's interior. However, directly observing this phenomenon remains impossible with our current technology. At Neptune's core lies a region roughly the size of Earth, composed of rock and metal heated to temperatures around 9,000 degrees Fahrenheit. This core formed first in Neptune's history when the young planet pulled together from the swirling disk of material that surrounded our infant sunday. The immense pressure at the core, about 8 million times Earth's surface pressure, keeps the rock and metal compressed into a dense sphere. One of Neptune's most puzzling characteristics is that it radiates about 2.6 times more energy into space than it receives from the Sun. Jupiter and Saturn also emit more energy than they receive, but their heat comes primarily from leftover warmth from their formation, still slowly leaking out after billions of years. Neptune lost most of its formation heat long ago given its smaller size and greater surface area to volume ratio. So where does this extra energy come from? The most widely accepted explanation involves differentiation, the process where heavier materials sink toward the center while lighter materials rise. As heavier substances descend through Neptune's interior, they release gravitational potential energy that converts into heat. This ongoing process, happening imperceptibly slowly by human standards but continuously over eons of time, generates enough warmth to power Neptune's heat output. This internal heat source drives the fierce storms and powerful winds that characterize Neptune's weather, creating atmospheric dynamics far more energetic than the weak sunlight alone could sustain. Neptune possesses the most violent winds known in our solar system. These jet streams race through the planet's upper atmosphere at speeds exceeding 1,000 miles per hour, far faster than any hurricane on Earth and even faster than the speed of sound in Neptune's thin upper atmosphere. Understanding why such extreme winds exist on a world that receives so little energy from the sun has challenged planetary scientists. Earth's winds derive their energy primarily from solar heating. The sun warms the equator more than the poles, creating temperature differences that drive air circulation. Neptune, however, receives less than 1,000th the sunlight that Earth does, making solar heating seem insufficient to power such energetic winds. Yet Neptune's winds blow with ferocity that dwarfs anything in our experience. The answer lies in Neptune's internal heat. As we discussed, the planet radiates more than twice as much energy as it receives from the sun. This heat flowing up from the interior provides the primary energy source for Neptune's atmospheric dynamics. Imagine a pot of water heated from below. The water at the bottom warms up, becomes less dense, and rises, while cooler water descends to take its place, creating circulation patterns. Neptune's atmosphere works similarly, but on a planetary scale and with far more energy available. The winds on Neptune blow primarily in an eastward direction, the same direction the planet rotates. However, some jet streams flow westward, moving opposite to the rotation. The fastest winds occur in the southern hemisphere around 30 degrees south latitude, where wind speeds regularly exceed 1,200 miles per hour. To put this in perspective, Earth's fastest winds, found in the jet stream, typically reach around 200 miles per hour. Neptune's rapid rotation contributes to organizing these winds into distinct bands. The planet completes one rotation in about 16 hours, spinning quickly enough that the Coriolis effect, which deflects moving air, becomes very strong. This effect helps organize atmospheric circulation into east-west bands at different latitudes, similar to but more extreme than the bands visible on Jupiter and Saturn. In 1989, when Voyager 2 flew past Neptune, it observed several large storms. The most prominent was the Great Dark Spot, an Earth-sized storm system similar to Jupiter's Great Red Spot. This dark oval rotated counterclockwise and drifted westward relative to Neptune's overall rotation. Bright white clouds, likely methane ice crystals, formed around the edges of the storm where air rose and cooled. Interestingly, when the Hubble Space Telescope observed Neptune 5 years later, the Great Dark Spot had vanished. However, a new dark spot had appeared in the northern hemisphere. Since then, astronomers have observed several dark spots come and go, suggesting that unlike Jupiter's Great Red Spot, which has persisted for centuries, Neptune's large storms are transient features lasting only a few years. Think of Neptune's atmosphere as an engine powered from within rather than from above. The internal heat provides a steady flow of energy that rises through the atmosphere, creating instabilities that grow into massive storm systems and drive the high-speed winds. The weak sunlight contributes some additional energy and creates subtle temperature variations between day and night, summer and winter, but the internal heat dominates the energy budget. These winds accomplish something remarkable. They mix and homogenize Neptune's atmosphere, distributing heat and chemical compounds across different latitudes and altitudes. This mixing helps maintain the planet's uniform appearance and relatively simple banded structure compared to the more chaotic patterns seen on Jupiter. Neptune takes 165 Earth years to complete a single orbit around the Sun. This means that each season on Neptune lasts approximately 41 years. If you were born during Neptune's summer, you would be middle-aged before autumn arrived. This extreme seasonal length creates atmospheric changes that unfold on timescales vastly different from anything we experience on Earth. Like Earth, Neptune has seasons because its rotation axis is tilted relative to its orbital plane. Neptune's axis tilts at about 28 degrees, slightly more than Earth's 23.5-degree tilt. This tilt means that during Neptune's northern summer, the North Pole points more directly toward the Sun and receives more sunlight, while the South Pole spends more time in darkness. 41 years later, the situation reverses. However, Neptune's seasons are peculiar for several reasons. First, because Neptune is so far from the Sun, the seasonal variation in sunlight is less dramatic than you might expect. The Sun appears as merely a bright star in Neptune's sky, about 900 times dimmer than it appears from Earth. Whether that dim star shines more directly on the northern or southern hemisphere makes only a modest difference in the amount of energy received. Second, Neptune's internal heat source partially masks seasonal effects. While Earth's weather and climate are driven almost entirely by solar heating, Neptune's atmosphere receives most of its energy from below. This internal heat source doesn't vary with seasons, providing a constant background of energy that moderates seasonal temperature changes. Despite these factors, astronomers have detected seasonal changes on Neptune. Observations from the Hubble Space Telescope spanning several decades show that Neptune's southern hemisphere, which has been experiencing summer, has gradually brightened. More high-altitude clouds have appeared, suggesting increased atmospheric activity. Meanwhile, computer models predict that as Neptune's seasons progress, patterns of cloud formation and storm activity should shift between the hemispheres. The seasonal changes also affect Neptune's moons, particularly Triton, the largest. Triton has its own thin atmosphere and, being tidally locked to Neptune, it experiences seasonal changes based on Neptune's position in its orbit. As different parts of Triton receive varying amounts of sunlight over Neptune's long year, ice sublimate from warmer regions and condenses in colder ones, slowly redistributing material across Triton's surface. Observing seasonal changes on Neptune requires patience and dedication. A graduate student who begins studying Neptune's seasonal variations at the start of their career would need to continue observations for their entire professional lifetime to witness the transition from one season to the next. This presents both challenges and opportunities for astronomers. The challenge is maintaining consistent observations over many decades. The opportunity is that Neptune provides a laboratory for studying atmospheric dynamics operating on timescales much longer than typical weather patterns on Earth. Think of watching plants grow. If you check hourly, you see no change. But watching daily or weekly reveals their gradual development. Neptune's seasonal changes occur on an even longer timescale, invisible day to day or even year to year, but becoming apparent when observations span decades. The slow pace of Neptune's seasons also means that each hemisphere spends decades at a time experiencing similar conditions. The storms, winds, and cloud patterns we observe today represent a snapshot of Neptune's southern summer, conditions that have prevailed for decades and will continue for decades more before autumn's gradual transition begins. Future generations of astronomers will witness Neptune's atmosphere transform as the seasons progress, comparing their observations with ours and building an understanding of how this distant world changes through its long year. Neptune possesses a ring system, though these rings are so dark and tenuous that they remained undetected until the Voyager 2 spacecraft flew past in 1989. Unlike Saturn's brilliant rings, which reflect sunlight so efficiently that they outshine the planet itself when viewed edge-on, Neptune's rings are faint and ghostly, composed of material darker than charcoal. The ring system consists of 5 main rings, each named after scientists who contributed to Neptune's discovery or study: Gale, Leverrier, Lassell, Arago, and Adams. The innermost ring, Gale, is faint and broad, beginning about 2,500 miles above Neptune's cloud tops. The outermost ring, Adams, lies about 39,000 miles from the planet's center and displays the most interesting structure. Adams' ring contains several bright arcs rather than forming a uniform ring. These arcs, given names like Liberté, Égalité, and Fraternité, appear as bright clumps of material concentrated in specific sections of the ring. When these arcs were first detected from Earth before Voyager 2's arrival, astronomers were puzzled. Ring material should spread out evenly around a planet due to the varying orbital velocities at different distances. What could hold these arcs together? The answer involves gravitational resonances with Galatea, a small moon orbiting just inside the Adams ring. Galatea's gravity creates a pattern of stronger and weaker gravitational pull at different points around the ring. Particles in the ring move slightly faster or slower depending on their position relative to Galatea, and this causes them to bunch together in specific locations. Think of it like people walking around a track at slightly different speeds. Most of the time they spread out, but if something periodically gives them a gentle push, they might bunch together at certain points. Neptune's rings are incredibly dark, reflecting only a few percent of the light that hits them. They appear to be made of material rich in organic compounds, perhaps similar to the surfaces of some asteroids and comets, which have been darkened by exposure to radiation and the solar wind over billions of years. The particles making up the rings range in size from microscopic dust grains to boulders several yards across. Several small moons orbit among and near Neptune's rings. These moons, including Naiad, Thalassa, Despina, and Galatea, are all irregularly shaped and relatively tiny, with diameters ranging from about 30 to 100 miles. They orbit Neptune in less than a day, racing around the planet at speeds of several miles per second. These inner moons probably formed from material left over after Neptune itself formed, material that gradually coalesced into these small bodies. Some of these small moons may act as shepherd moons, using their gravity to help confine ring material and prevent it from spreading out or falling into the planet. However, Neptune's ring shepherding appears less efficient than Saturn's. The rings are quite diffuse and seem to be relatively young in geological terms, perhaps only a few 100 million years old rather than as ancient as the planet itself. Occasionally, collisions between small moons or between moons and larger particles may shatter these bodies, creating debris that replenishes the rings. Without such replenishment, the rings would gradually fade away as particles spiral into Neptune or are knocked out of orbit by various perturbations. The existence of the rings today suggests that this replenishment process continues, with small moons slowly grinding themselves away to create the ghostly rings we observe. Triton, Neptune's largest moon, is one of the most fascinating worlds in our solar system. About 2,000 miles in diameter, roughly 3/4 the size of Earth's moon, Triton orbits Neptune in the opposite direction that the planet rotates. This backward or retrograde orbit immediately tells us something remarkable. Triton did not form alongside Neptune. Instead, this moon was captured, pulled from an independent orbit around the Sun into servitude around Neptune billions of years ago. In the solar system's early days, the region beyond Neptune contained countless icy bodies, remnants of the planet-forming disk that never coalesced into a major planet. This population still exists today as the Kuiper Belt, though it has been greatly depleted over time. Triton likely originated as one of these Kuiper Belt bodies, possibly similar to Pluto, before a gravitational encounter with Neptune millions or billions of years after the planet's formed caused it to be captured. The capture process was violent. Triton would have approached Neptune on some arbitrary trajectory, and through a combination of gravitational interactions, possibly involving other moons or bodies that no longer exist, it lost enough energy to become bound to Neptune. Initially, its orbit would have been highly elliptical and tilted at a random angle. Over hundreds of millions of years, tidal forces gradually circularized the orbit and, crucially, converted the orbital energy into heat within Triton's interior. This tidal heating was intense. Imagine repeatedly flexing a piece of metal back and forth. It becomes hot from the internal friction. Triton experienced this on a planetary scale as Neptune's gravity flexed and squeezed it during each orbit. This heating likely melted Triton's interior completely, causing the moon to differentiate into a rocky core surrounded by a thick mantle of liquid water and other ices. The surface may have been an ocean for a time before cooling and freezing into the icy crust we see today. Modern Triton is a frigid world with surface temperatures around -390 degrees Fahrenheit, making it one of the coldest surfaces in the solar system. Yet this frozen moon is geologically active. When Voyager 2 flew past in 1989, it observed geysers erupting from Triton's surface, blasting plumes of nitrogen gas and dark organic particles up to 5 miles high. These plumes then drifted downwind in Triton's thin atmosphere, creating dark streaks across the icy plains. The geysers likely formed through a greenhouse effect. Sunlight penetrates Triton's relatively clear nitrogen ice crust and warms darker material beneath the surface. The nitrogen ice at depth absorbs this heat and sublimates, turning directly from solid to gas. As pressure builds, the gas eventually breaks through weak points in the crust and erupts as a geyser. Think of a pressure cooker where steam builds up until it finds a release valve. Triton's surface displays diverse terrain. Some regions are covered with smooth plains of frozen nitrogen, while others show cantaloupe terrain, a unique landscape of oval depressions and ridges unlike anything seen elsewhere in the solar system. Still, other areas preserve signs of ancient geological activity, including what appear to be frozen lakes and possible cryovolcanoes that erupted slushes of water and ammonia rather than molten rock. Because Triton orbits Neptune backward, tidal forces continue to act on it, but now they remove energy from the orbit rather than circularizing it. This means Triton is very slowly spiraling inward toward Neptune. In a few billion years, Triton will cross the Roche limit, the distance at which Neptune's gravity will tear it apart. When this happens, Triton will be destroyed, and its material will spread out to form a spectacular ring system around Neptune, far more impressive than the modest rings that exist today. Every detailed image of Neptune, every measurement of its atmospheric composition, every discovery about its rings and moons, comes from a single spacecraft encounter lasting only a few hours. On August 25, 1989, Voyager 2 became the first and, so far, only spacecraft to visit Neptune, flying within 3,000 miles of the planet's cloud tops during its final planetary encounter after a 12-year journey through the outer solar system. Voyager 2 approached Neptune from below the ecliptic plane, the imaginary sheet on which most planets orbit. This trajectory allowed the spacecraft to study Neptune's atmosphere, rings, and magnetic field before making its closest approach. The spacecraft's cameras captured images showing the Great Dark Spot, bright methane clouds, and the banded structure of the atmosphere. Instruments measured temperature, pressure, and composition at different levels of the atmosphere and detected Neptune's offset magnetic field, which is tilted 27 degrees from the rotation axis and offset from the planet's center. After passing Neptune, Voyager 2 flew within 2,500 miles of Triton, capturing the only close-up images we have of this fascinating moon. These images revealed the geysers, the varied terrain, and the incredibly smooth surface with very few impact craters, suggesting recent geological resurfacing. Then Voyager 2 departed, heading out of the solar system on a trajectory that will never bring it close to another planet. Since 1989, all our observations of Neptune have come from telescopes on Earth and in Earth orbit, primarily the Hubble Space Telescope. These observations have tracked seasonal changes, monitored the formation and disappearance of dark spots, and studied variations in Neptune's brightness and color. However, telescopic observations have limits. Even Hubble cannot resolve details smaller than a few hundred miles across on Neptune, and spectroscopic measurements from such distances provide only bulk averages of atmospheric composition and temperature. Many questions remain unanswered. What causes Neptune's vivid blue color to be so much more intense than Uranus's? What is the exact structure and composition of the interior? How do the winds maintain such high speeds? What drives the formation and dissolution of the large dark spots? How does Triton's geology work in detail, and what might liquid layers exist beneath its frozen crust? Several mission concepts have been proposed to return to Neptune. One idea involves an orbiter that would spend several years studying the planet, watching seasonal changes unfold, mapping the magnetic field in detail, and repeatedly flying past Triton and the other moons. Another concept suggests a probe that would descend into Neptune's atmosphere, measuring temperature, pressure, and composition directly as it falls through the cloud layers before being crushed by the increasing pressure. Such missions face significant challenges. The journey to Neptune takes at least 12 years with current propulsion technology. The immense distance means communication signals take more than 4 hours to travel each way between Earth and a spacecraft at Neptune. The weak sunlight at Neptune's distance makes solar panels impractical, requiring spacecraft to use nuclear power sources. These factors make missions to Neptune expensive and technically demanding. Yet the scientific rewards would be profound. Understanding Neptune helps us understand how giant planets form and evolve. The planet's internal heat source, powerful winds, and active moon system raise questions relevant to the study of planets around other stars. Many of the thousands of known planets orbiting other stars appear to be Neptune-like worlds, making our ice giant a crucial reference point for understanding planetary systems throughout the galaxy. For now, Neptune remains mysterious, visited once and watched from afar, its secrets guarded by distance and time. And on that note, we reach the end of our peaceful journey to Neptune. We've traveled nearly 3 billion miles from home to explore a world of deep blue clouds and 1,000-mile-per-hour winds, a planet that generates its own heat and wears a set of dark, ghostly rings. We've descended through layers of atmosphere where the pressure grows intense enough to form exotic states of matter and perhaps to rain diamonds from compressed methane. We've witnessed storms the size of Earth that appear and vanish over the course of years, and we've considered seasons that last longer than most human lifetimes. We explored how Neptune was discovered through mathematics before it was seen with human eyes, a triumph of prediction that extended the known solar system by more than 1 billion miles in a single night. We learned why Neptune glows with such a vivid blue color, deeper and richer than any other planet, a hue created by methane in its atmosphere and enhanced by substances we're still working to identify. We examined the planet's interior structure, that strange realm where ices behave as liquids and carbon atoms may crystallize into falling diamonds. We marveled at winds that race faster than the speed of sound through an atmosphere powered not by sunlight but by heat rising from below. We contemplated the glacial pace of Neptune's seasons, each one stretching across 4 decades, creating atmospheric changes that unfold on timescales requiring generations of astronomers to observe. We discovered rings made of material darker than coal, held together by the subtle gravitational influence of small shepherding moons. And we met Triton, the remarkable captured moon that orbits backward and erupts geysers from its frozen surface despite being one of the coldest places in our solar system. We learned that Triton is slowly spiraling toward Neptune and will one day be torn apart to form a magnificent ring system far grander than anything surrounding the planet today. Perhaps most remarkably, we recognize that all our detailed knowledge of Neptune comes from a single spacecraft encounter lasting only a few hours more than 35 years ago. Since then, we've watched from afar, tracking changes through telescopes but unable to return for a closer look. Neptune holds countless mysteries still waiting to be explored, questions that will require future missions and future generations of scientists to answer. Neptune reminds us of the vastness of our solar system and how much remains to be discovered. This distant world, spinning in near darkness at the edge of the planetary realm, conducts its own grand experiments in atmospheric physics, planetary geology, and celestial mechanics. Every measurement we make, every image we capture, adds another piece to the puzzle of how planets work and how our solar system came to be. Thank you for joining me on this exploration. I hope you found it peaceful and perhaps even learned something new about this distant ice giant. Whether you're drifting off to sleep or simply enjoyed some time contemplating the cosmos, I'm grateful you chose to spend this time with the nocturnal astronomer. If you have thoughts about Neptune or suggestions for future topics you'd like me to cover, please leave them in the comments below. And if you enjoyed this journey, remember to give it a thumbs up and subscribe so you won't miss future explorations. Until next time, keep looking up.